I'm Kyle. I will be talking about Obstore, a library I wrote to really efficiently access data on the cloud. So AWS S3, Google Cloud Storage, and Azure Storage are the backends that we use most for object storage in Cloud Native Geo. But by default, if you use the Python libraries that are provided by those vendors, Boto 3, Google Cloud Storage, and Azure Storage, then you have to develop your own abstraction level on top of it if you want to use more than one, or if you want the ability to move to a different provider in the future. Instead, it's really nice to have the option to have Python libraries that do this abstraction for you, to have FSPEC or Obstore have these APIs that you don't have to change your code, you can write it once to access data on whatever backend. So first, we'll go into some of the ways that FSPEC and Obstore are different or are compared. First, how they're something that is similar with both of them. They have a lot of supported backends, though in the Obstore case, Obstore intentionally has a smaller scope to handle 99% of what we actually use, in particular S3, Google Cloud Storage, Azure Storage, and S3 compatible providers. So stuff like Cloudflare R2 also works with this because it uses the S3 API. Whereas FSPEC supports a lot of kind of sometimes very peculiar ones like Dropbox or Google Drive that we don't necessarily need for our cloud native geospatial work. But then into the ways that Obstore and FSPEC are really different. First, they have a different abstraction target and level of abstraction. That FSPEC really tries to emulate object storage as files. So if you look at this code sample on the bottom left, S3FS opens this file-like object that then presents like a Python file-like object API that doesn't exactly match how object storage is actually used and how you actually get the data from object storage. That is much closer to HTTP requests, and there's elements of object storage that can't really be represented as a file. So stuff like operation preconditions, if you only want to fetch a data if that data has changed, or atomicity to make sure that if you failed with a write, that data actually can't be read. Obstore tries to emulate this a lot differently, much closer to HTTP requests. And the clearest way that this is different is in the stateful versus stateless nature of FSPEC and Obstore. So here, in each of these screenshots, we are doing a list of an S3 bucket twice. Now, what happens in each of these instances? With a stateful API, you don't necessarily know what is actually happening under the hood. So for example, is the list request cached? How many requests are actually being made? What happens if the remote data changes? And if the data changes, does the second list automatically reflect that data? And for here, in the FSPEC case, it only makes one request, that it does cache under the hood. And that means that there isn't as much of a direct mapping between what method you call and what actually happens under the hood. And so sometimes it's uncertain what is going on. Whereas in the Obstore case, whenever you call list, it directly maps into the HTTP request. And so if you call list, it makes a method, it makes an HTTP call. This also changes how big the API surface is for each of these libraries. FSPEC has a much larger API surface. It has dozens of public methods in the abstract file system, which is what something like S3 file system implements. And it's also common to hit something like a not implemented error because a lot of the FSPEC backends don't necessarily implement all of the common file system operations. In contrast, Obstore has a really simple API that has only 11 methods that are a lot easier to understand. 11 kind of synchronous, and then they're asynchronous copies. It also means that it's very clear when you call a Python method what is actually happening. So when you open an FSPEC file and then iterate over the bytes in that file, what is actually happening? Is that multiple requests? Like how many HTTP requests are actually made from that? Whereas with Obstore, it only is a single HTTP call whenever you call like obstore.get. This means that there's no automatic caching as part of Obstore. It's something that we could add on top, but it means that you're not kind of having to guess what caching happens outside of the APIs that you're directly interacting with. And so it's very rare as well, because it has a smaller API, to have these not implemented errors that are something that you hit at runtime instead of kind of in advance. And so Azure suffix requests is an example here, because Azure doesn't support getting like the last 20 bytes of the file, but that's kind of a rare case where you don't where you get a not implemented error. And so here's the entire Obstore API. Is very simple, easy to understand methods. Copy an object inside a single bucket, delete, get, head, list, put. Very similar to these HTTP verbs that you might be familiar with as well. And that's it compared to FSPEC's 56 public methods. The number of dependencies, the number of Python dependencies changes as well between FSPEC and Obstore. FSPEC uses the native vendor official libraries, so it makes a Python wrapper around Boto 3, Google Cloud Storage, and Azure Storage. This means that it has a bunch of transitive dependencies. So GCSFS, for example, has 31. And it also can be hard to get a version in your environment of these underlying libraries that are compatible with all of each other. Especially, I know people have hit issues with Boto 3, AIO Boto Core, and such in the past. Whereas Obstore doesn't have any Python dependencies at all that are required, even to access both S3, or all of S3, Google, and Azure. And that's because it took me a while to understand this. Well, it's because it uses this Rust library under the hood. So all of the dependencies are kind of abstracted from the Python user. You don't have to have Python dependencies in your environment. It's the Rust developer, me, who has to handle which dependencies can compile together to work together. But something I didn't understand for a while is that when you see an S3:/ bucket path, it's not a different protocol. It's not a different way of actually accessing the data. It's just syntactic sugar for saying you're using HTTP, but here's the specific method that you should use for authenticating these HTTP requests. And so you don't actually have to use one of the AWS native libraries for accessing AWS. The Object Store Rust library, which is an open source Apache project, just uses an off-the-shelf Rust HTTP client and then implements this authentication process so that if it sees the S3 protocol, it knows how to make those requests against the S3 HTTP API. Another part is streaming, where FSPEC, where streaming is really defined as being able to start working with the result before you wait for the entire result to finish. Where streaming download, as far as I can tell, FSPEC doesn't support a streaming download where you make one request and then can work with that data. You have to download it maybe to a file and then use it, or materialize it all in memory. And list, similarly, will return all objects with that prefix without being able to do something without waiting for it to finish. Whereas Obstore has full sync and asynchronous streaming support. So with a download, you can make only one request, just like an HTTP download, and you get a stream of bytes. So that's exposed in Python as either a synchronous or asynchronous iterator. With a list, similarly, you get automatic pagination behind the scenes. So you never have to paginate yourself over different lists results that come back from S3. And if you just keep calling that iterator, you'll get more and more results. So as a little bit of code, here's an example of taking a local store instance, calling get, and then all you have to do is iterate over the response, and you get the bytes from that streaming download. And only a couple changes, we can get that fully async. So this is an asynchronous first request that just, this line 5 doesn't wait for the entire data to be downloaded. It only validates that that file actually exists, make sure that the HTTP request succeeds, and then presents an async iterator that never blocks the main thread and is able to really efficiently get data into your machine. And similarly, you can connect the streaming download and the streaming put. And to say, if you want to download files or have a proxy to connect an HTTP or S3 or Azure store, this streams the data through your machine so that it never uses more memory usage than something you can configure. By default, it's like 20 or 30 megabytes. And even if the data is a gigabyte or 100 gigabytes, it'll be able to stream that from the download directly into the upload. And similarly, the list, you just keep iterating, you just keep using that for loop, and you get all of the data without having to wait for all of the data to come in. One of the other ways that Obstore really excels is that I'm a big fan of types. I'm a big fan of, I believe that types make it easier to develop, easier to understand an API, easier to not have to actually read the documentation, because who actually reads documentation? But you can just kind of page through what shows up in VS Code and understand how it should be used. And so here, anywhere that Obstore can have type hints, it does have type hints. So if you are creating an S3 store, you get the list of possible regions that you can autofill. And on the right side, you get all of the possible configuration options on the top right, and it'll type check all of the parameters that you pass in. So in this case, it expects a Boolean, you pass in a string, and you get a type error in your editor. Similarly, for parameters, you get the options that are available. And for results, everything that can be type hinted is type hinted so that it integrates really well into modern Python development. A couple other highlights that I really want to show off. Well, I say that, and then here, actually, you could look at the docs for how to construct stores. There's a bunch of different ways to do this. If possible, you can use the latest on that screen, line 13, that lets you pass any sequence of configuration parameters into the S3, and it's very similar for Azure or Google Cloud Storage. But one of the things that I'm really happy with in Obstore is how well it handles authentication, because there's such a long tail of authentication that it's kind of hard for any library to do this perfectly. But in addition to these native credential support that if you pass in an access key ID, or if you have stuff in your environment, it'll automatically pick that up. You can also pass in an arbitrary Python callback that can be any function that, as long as you are able to get your S3 or Google or Azure credentials, you can do whatever authentication method you need. And one of the cool things here is that it'll automatically refresh your tokens if they expire before expiration without you ever having to think about it. So for example, one of the credential providers that we natively support is this NASA Earth Data credential provider. That NASA Earth Data has in-region direct bucket access, but it only has short-lived 1-hour tokens. And so if you have a job that lasts 3 hours, then otherwise you'd have to make sure that your code stops in the middle, you get a new token, and your code uses that new token. Whereas here, Rust will automatically update, or the internals of this library will automatically do that without you having to think about it. And so after about a year of development, we got this Obstore backend merged into Zar Python. It was a collaboration with a lot of people from the Zar community. Big shout out as well to my colleague Max Jones, who helped push this integration over the line. This shipped in Zar 3.0.7, which came out a week or two ago, so you can test this out yourself. And here's a cool example of all of these pieces coming together, where this is, except for the imports, this is the entire sequence of code to get this output on the bottom right, where this uses data from the planetary computer, where it uses this planetary computer credential provider, another of the default credential providers that Obstore supports, where there's no authentication happening here that the user has to pass in. This will automatically use anonymous authentication against the planetary computer SAS token APIs. and then pass that into the Zar API and into Xarray, and we can visualize this Zar data set. And similarly, the planetary computer also integration also has automatic token refresh. So you don't have to worry about your tokens expiring and have to think about that at all. Then on the performance side of Obstore, thanks to Max Jones, again, my colleague, who's been helping with benchmarking for Obstore and the new Zar integration. So here on the left, this is a graph of loading a 24 gigabyte array into Zar or into Python through the Zar Python API. And we get 3 times faster wall time by using Obstore as the backend instead of the default FSPEC backend. And here, the benefit of Obstore is really when you have a large amount of data and a large amount of concurrency and a large amount of files that you're requesting at the same time. And so Zar has thousands of files probably under the hood in this query that Obstore can fetch that very efficiently in its concurrent APIs. Whereas opening the data set and doing a single point query are maybe only slightly faster because you're not actually doing that much cloud operations under the hood. And then here is another view of Jeff's graphs and Jeff's data from the last presentation, where this is benchmarking just raw request throughput with Obstore, AIO HTTP, AIO Boto3, and requests. And we find that the throughput is among the highest of Obstore for AIO HTTP, and so it seems that Obstore is at least like among the fastest HTTP client in Python, let alone HTTP client that also knows how to access S3, Google, and Azure. And then why is it faster? First, we have to really define like what is fast. And one of the elements of fast is latency. And there is nothing that really any Python library can do to make your latency faster. That's your network conditions for how fast you can access the first byte of data from cloud storage. But we can make a dent into the throughput, the total amount of data that you can fit through the network pipe at a time. And we believe that Python overhead can prevent this full hardware utilization. And so especially when you're making like 1,000 requests, that'll happen a lot faster compared to having, compared to a backend that doesn't handle the concurrency as well. Though it is also important to know that the Rust side that Obstore builds on top of has a multi-threaded Rust event loop. So even though your Python code is single-threaded, it uses by default, we'll allow customization of this in the future, it allows for multi-threads on the Rust side. And then so far in this talk, I've only talked about a Python API, Obstore as a Python API. But it's actually only half of this project because there's a lot of other great Rust libraries out there that would also love a Python component to their own custom way of accessing object storage. And so there's a lot of projects out there that use this Rust object store library. Async TIFF, I worked on, it's not production ready yet, but I wrote async TIFF as a cog reader in Rust that featured in Jeff's benchmarks before. And that uses the same internals of Obstore to be able to work with data on S3, Google, and Azure. And GeoArrow RS, it isn't, I've been working on updating it, but it'll have reading and writing of GeoParquet, including the latest 1.1 support in Python. And it uses, again, the same internals to be able to access the data on remote storage. So we can see that just as we get great performance in Obstore, we can, by having this Rust Python API that we expose to other Rust developers who want to have their own Python API, we can have better performance than a Python, or here, this is Raster.io, but we can let other people also have that great performance. And thank you. Thanks to Jeff and Max for helping benchmark. Zar community was amazing for helping get this integration merged. And thanks to the Rust database community for creating this library to start with. We have a break after this, so basically anybody who wants to stay and ask questions of Jeff and all of us can stay, and if you don't, you can go have some snacks. But any questions?
Thank you. Well-organized presentation. So two questions here, but you can decide to just take one to give time for the others. So first one is, are there any limitations you're aware in terms of streaming async calls? And then the second one is, how robust is the failover handling of the requests?
What's the second question again?
Yeah, how robust is the failover? If
How robust?
the request fails, how you guys handle that?
Yeah. Sorry. What was the first? Or sorry, I'll do the second question first. There is a way to retry. There's a configuration that you can pass in that will automatically retry the requests if they fail, and it'll use exponential backoff by default. So you can customize that. And sorry, what was
the first one is the concurrency limitations.
Concurrency limitation, yeah. The main concurrency limitation is that there's a timeout by default of 30 seconds. And so if your request takes longer than 30 seconds, by default, it'll error. And so you can set the timeout manually, but otherwise there's no issues with high concurrency streaming that we've hit so far.
Okay, great. Thank you.
And also, if anybody has more questions for Jeff, you can use this time.
I have a question. I guess it's for Jeff and Kyle. So Jeff, Kyle only showed the initial header benchmarks, but you showed benchmarks for kind of full lifecycle access across the cog. Do you have a good understanding of what the smart coalesce that's happening on the BSI side is, or with any of the other libraries? So that's the first part of the question. And then second part is, Kyle, when we want to introduce smart coalesce, where do we put that? Do we put that in Obstore, or do we put that in some kind of abstraction above Obstore?
I missed the library name in your question. You said in smart coalesce in something.
Coalesce, yeah, okay. In all of them, in all of the VSI requests you did, and then I guess because do you know, you don't necessarily know what your individual calls are being dispatched as an HTTP call, right? You don't know how that request gets mapped into individual HTTP requests, right?
Well, it depends what you're using. I think if you're using Rasteria, you have a lot less control over that. You can set environment variables and you can make your cog in a very specific way. But I've seen rounding errors cause GDAL to fetch an extra row down. One of the advantages of AIO HTTP or rolling your, I think you have less control over Obstore. If you're writing your own Python using AIO HTTP, you of course have as much control as you want in terms of how that coalescing is done. Right now, if you look at async TIFF, the coalescing is managed by async TIFF. So there's that library exposes a fetch tile API, which you pass a single tile and you get back a single tile, and fetch tiles, where you pass in essentially a matrix of tiles you want to request, and it's just smart enough to know if there are two tiles that are adjacent to each other, it should coalesce. My personal opinion on this topic is you should give the user as much control as possible over what ranges are actually being sent. And so you should, I think maybe the Obstore the initial fetch ranges or fetch tiles API in Obstore is really nice because it just works. I would like something a little lower level, just me personally, because I like having control over everything I'm doing when it comes to how I'm interacting with the Obstore. That definitely helps a lot when you're caching, because you have a lot of control. Caching range requests is notoriously difficult to do, and when you don't have control over how that coalescing is happening, it gets even more difficult.
Yeah, and in particular, in both Obstore and async TIFF, it's the network layer that chooses how to coalesce the requests. And so right now it's hard-coded on Obstore, but we could change that. You can make an issue, remind me. But right now that's hard-coded, and similarly in async TIFF, you just choose, say it might be 1 megabyte right now, and if you're making two requests that are closer to each other than 1 megabyte, then they'll automatically be coalesced.
Yeah.
But we could make that configurable.
You could set that to 0 if you want to have total, yeah.
Yeah, let's talk about, we'll file an issue. Thanks.
one question for Jeff about caching strategies. There's a really good analysis of the different options. There was one more that I was wondering if you had explored, and I don't know which load balancers and public clouds support this, but were you able to test a scheduling hash-based?
No, I was not.
Okay.
No.
Because
Go ahead.
I think like one way to mitigate the issue of your request being bounced to different cache servers is to say, here's a hash, which is, for example, based on my request path. Please try to route me to the
Yeah, and
server.
I think actually, so a group cache, the peer-to-peer cache, it uses a consistent hash. That's how it manages. That's how it manages hot versus cold keys. And so, yeah, I could definitely see that strategy working really well. I also don't know if anybody supports that type of load balancing. Most people just do round robin, and I chose round robin just because it's the most simple to explain in like a conceptual setting. But yeah, there are definitely smarter ways of assigning data to replicas or assigning data to different nodes, especially when you're running jobs that are so memory intensive they don't fit on one node.
Sure.
Yeah.
Yeah, thanks for your tips.
Another thing that I've done in the past in my career is you can order data, like if you have a lot of polygons and you're summarizing a lot of cloud-optimized geotiffs, you can pre-partition your polygon, so all the requests for all the polygons that fit within a single cog are processed by the same node. You can do stuff like, if you have a lot of points that you want to intersect with a cog, you can order them on a Hilbert's curve, right? So that you're generally sending points that are closer to each other at the same time. Yeah, there's a ton of stuff to dive into on ordering and load balancing and routing requests around in an optimal way. Yeah. I would love to spend months of my life looking into this. Yeah. You could spend months looking into all this if you really wanted to.
Can I just
Any
say
other
I'm
question?
so
Yeah.
glad that there's people like you two focusing on these features. I totally can't do it.
Well, it's great because Kyle was like, I don't know. Kyle's like, I'm kind of scared of DevOps and like, and I'm scared of Rust. So it works, and I love DevOps, so it's like, it works out pretty well. Yeah, yeah. At one point, you're like, this is a good division of labor.
Yeah, this is excellent. I didn't have to do any benchmarking, and it just
And I was up until 2:30 in the morning debugging why FSPEC was ooming my instance last night.
Service API calls.
Sorry?
It's one of the 56 service.
Yeah, I have no idea. I think it was related to the connection pooling, actually, in some weird way. But I went to bed. Cool. Thanks, guys.
Thank you.